You know what? Why not? Let's do this daily. We'll go in blind on a hard one. Let's see if we can do this. Convert a non-negative integer num to its English words representation. I like how this one's kind of simple. I imagine that means it's gonna be really hard. So we have num 123, and there's no ands, which I like. That's one less complication. It's not 12,325. Well, and 45. So, what's in a number? What's in a number? Um, we're not doing decimals, I'm assuming. Okay. Yeah, nums has to be greater than or equal to 0. So if it's greater than 0, my first consideration is that we have to ignore any zeros that pop up unless the number itself is 0. Because you would never say 1,000,000. If it was 1,000,000, it's not 1,000,000,000,000 000, so on. You just say 1,000,000. So maybe this is kind of skating around a central concept. But first, let's just say if num equals 0, return 0. Okay? So that's the only situation where 0 pops up. Other than that, we have to basically work our way up in decimal points, and then I think backwards concatenate. Because I think it's easier to backwards concatenate knowing that you had to start with like 1, you know? But if you work forwards, then you had to figure out how big the number is. And see, well, it goes up to 231. What's 231 again? It's, what was it? Million, 10 million, 100 million, billion. Okay, so the highest we're going to need to go is a billion. We could do a loop. We could do a loop that basically counts up, and every loop we do modulo to get the digit, the first digit, and then floor divide to shift it all down. So we do modulo 10 to get 5, and then once we have added the 5. So we'll return a string called English. All right. Now we're going to say while num. While num, because basically we're going to keep on dividing and dividing and floor dividing and dividing and dividing until it's 0. And once it's 0, this loop ends. Okay, so now we have to think about how we handle everything. For the ones, it's just, oh, you know what? Maybe we could do something similar to what I did with the Roman numerals, because we could just do there's only 10 digits that we would have to handle differently. So what if we did like 10? Because yeah, you can only go up to 231 is 2 billion. So that's 10 digits. So maybe that's only 10 conditions. Okay. So instead of while num, how about we start with if num modulo 10 is greater than 0. If this is the case, this is the ones digit. Because modulo 10, we know that if it's 0, then that'll already be the case. Otherwise, we had to ignore all zeros. Because you would never say 0 out loud. You don't say 1,000,000. So how about we do like nums modulo 10 is greater than 0. This means that we do have to say the ones digit out loud. Oh, 12,000? Are you serious? Interesting. Oh, this just got a lot harder. So we can't necessarily do it digit by digit. We can't do it digit by digit because the teens are what makes this hard. Every other digit just has, well, so like every other place, well, like 20 through 99 have two separate words. But for special cases, dang. So this is a matter of, I feel like this would be good with like pen and paper. But this is a matter of just how do we sequence the questions that would lead up to that. So, how about well, the hundreds are always going to be blank 100. Okay, so 1 million. So I'm thinking like handling it in groups of threes. Okay, I'm gonna save you some time. I'm gonna just like work on this in silence and pause this, and I'll come back if I've started to figure something out. All right. Let's see. Not sure how much time has passed. Really doesn't felt that long. Maybe like 15 minutes since I paused it. I decided that this was gonna take a lot of like tinkering, and I didn't want. If you're watching this, I didn't want to put you through that. I'd rather show you my initial reaction, my initial thoughts, and then now that I have it solved, I'll go through my solution, which does pretty good on memory. Could be better on runtime, but really doesn't really. It kind of seems like a luck of the draw thing, considering mine used 41 milliseconds and like the top 50% maybe use like 6 milliseconds less. I don't know. I'm fine with that. Probably if I reran it, it would be faster. So first thing we have to do immediately is filter out zeros. Why? Well, The reason why is because if we have a zero, the only case that we're going to print out the word zero is if the number itself is zero, because the number in the description includes the number zero, less than or equal, well, greater than or equal to zero. But there's no other case in which that would pop up. So since that's the only case that would pop up, let's just do that as a little edge case, and then we can treat every number. Then otherwise we can just skip zeros, because we don't want to have to like consider, okay, well, we have a zero. Well, is it in the first place? Let's just skip all that. Let's just say if we have a zero, it's zero. Otherwise, skip all zeros. That's my logic there. Next, I made a quick dictionary of all of the different words that you would find when saying a number out loud. And I was just doing this based on the problem description. So thankfully there's no and it doesn't get tricky. It doesn't say like 1200 or something. It's 1200 if it's like 1200. So we need the numbers 1 through 10, obviously. Then we need the teens, because the teens are their own special thing. Like let's see. There's actually no example right here, but you wouldn't say 100 if you had 111. You wouldn't say 110 and 10 1. That's not a thing. You say 111. Let's see, and then you just need every tens place after that, because those all also have their special words. Otherwise, you can just go back to here. So ones digit, get the ones. Then you have the teens in case you group together the tens and the ones. Otherwise, you group together one of these tens places with one of the ones. And then when you get back up to the 100, you're back to the singular ones. So those are all the words that you're going to need. So digit to words. That's the map that I came up with. Now we have string concatenation. That's what we're doing here. We're starting with one big string, or starting with a string and then basically stitching onto it as we go. My logic was that it would be easiest to work our way upwards and basically add to it backwards. So do take the word, and then if we find, and then divide our way down to shrink the number with every decimal place. And if for every word that we find, we stitch a word beforehand. So like we have one, and then we check to see, well, are there any tens? And if there's a 10, then we say, okay, well, now the word is whatever that 1 was plus whatever the 10 is. So the first thing we have to do is, I kind of did this a little wonky, a little bit straightforward. It is the same chunk of code 3 times over, but I just kind of felt it easier in my head to do this. I mean, to be honest, right now, as I'm thinking about it, I could do it as like a loop, but that wouldn't really be that much better in my opinion, because it would only save us like a couple of conditions for the smaller numbers. I don't really care to do that now. But basically I have the same code 3 times over. The only difference is that it says million, thousand, and billion. Everything else is the exact same, but there's not that much of a difference. If anything, it's fast. Well, it's faster in some cases, because we don't have to worry about, we would have to worry about counting the number of loops, to worry about whether or not the next word is million or thousand or billion, if that makes sense. So let's start with here. We have to deal with the first 2 digits, and we have to deal with the first 2 digits at the same time, because they might be a teen. And so that, if it's 11 through 19, then we have to treat it as one word. So we can't just take the first digit and take it solo, because if it's 1-9, then we have to say 19, which is one word, as opposed to 10 and 9. So we had to check before we did the digits separately that they're not grouped together. So to do that, I do the modulo of 100 to get the first 2 digits of the number. All right, so we have modulo 100. That'll give us the first 2 digits. And I check if that's between 10 and, actually, should be greater than or equal to 10. I guess so. Because if it's 10, then it would still just be 10. We know that since there's a 0, then, I mean, I guess for that matter, we could just put this as 20. Well, less than or equal to 20. But yeah, that does not make a difference. This because if it's 10, then there's no ones place, and if it's 20 on the nose, then there's no ones place. Regardless, we take the teens digit, which is those first two numbers together, and we access the dictionary. And so if it's like, if the first two numbers are 15, then we would plug 15 into this and we get 15, and then we start that as our English word. Okay. Then if they're not grouped together, first we check that it's not zero, because we want to remember we want to ignore it entirely if it's a zero. You never want to say the word zero out loud. Um, and let's see. Yeah. Um, so you're do yeah. So we do the same thing just separately. And if so, we check for a ones digit by getting modulo 10, and then we get a tens digit by getting the number divided by 10. Oh, is that right? Yeah, the number divided by 10. So we shift it down, we get rid of the ones place, and then we do the modulo 10 of that, and then we do times 10. There's probably a quicker way of doing that, but yeah, that's just the quickest way to get to isolate the second digit for me. And then we multiply it by 10, because when we plug it in, if it's like 20, we want to make sure it says 20 and not 2. So if it's like 123, we need to make sure that we're plugging in 20 and not 2, because if it's one, then we would get 123 instead of 123. All right, so we do those separately, and we want to make sure to include some spaces. Now, if we just have like 30, then we will theoretically have a space beforehand, but that's why at the end we say R strip, and that'll remove all the trailing spaces and things that don't matter, in this case just white space. So we can get rid of that, and we have digits to word, digit to word, tens digit, and we stitch that on, and you see we stitch it on backwards. So we take the 1 and then we put the tens in front of that. All right, then we shift up to the hundreds, and we check if there's 100 by doing modulo 10, since we've now shifted by doing floor divide up to the hundreds place. We check if that is not a zero, because if it is a zero, we ignore it. And then we get the hundreds digit by doing modulo 10. And we just stitch that on to the word 100, and then whatever the first two digits were. If we have 1,000, then we just need to stitch 1,000 on, but then 1,000 could be, well, is determined by the prior three numbers. So we just need to make sure that there is 1,000, being that there is some number within the next three digits, because you could have 1,123. So it's those middle three digits. If you have like 1,000,000,123, then you would never say the word 1,000 out loud. So right now we're checking by doing modulo 1,000 does not equal 0. You're checking that there's at least one number, well, one non-zero within these three digits. So then we stitch on the word 1,000 right there. Okay, and then basically we just do the exact same thing, because it repeats. So we do check for a teen. So, you might have like 15,000. And if it's not a teen, then get them separately. Shift up to the 100. Check if there's, check what the hundreds digit is. Then check if there's a million in the same of the, you check 1,000, and then do the same thing over, except with a billion instead of a million. And then strip out the remaining white space, and we have code that works. And let me see if it actually works faster if I run it again. Yeah, what do you know? Let's go. 34 milliseconds. You could do it as a loop. You could. But then you have to make another dictionary or something to map, like, okay, it's the third iteration, so it'd be a billion. Instead of like 1,000. So you gotta worry about those every starting from the fourth digit. I don't know. Regardless, this works. I think that if you can avoid doing a loop, like if you can just do it straight up, it's nice. I mean, well, I don't know. It was less for me to think about, and it works just fine. So I'm really happy with how this came out. This was a really good problem. Was it a hard one? This was a hard one. This is actually my first hard one that I'm doing on the channel. Was it a hard one? Um, Honestly, I don't know. I think it was like a medium one with a hard length. I mean, I wrote like, 118 lines. Granted, it's because I didn't feel like doing a loop and there's a huge dictionary in there. Um, was it a hard one? I don't know. But, you know, maybe that's because I'm getting better and I just don't realize it. this was a really fun problem. I would really recommend doing this because it's yeah, it really just makes you think, you know, it makes you almost have to like relearn how numbers work and then how you express them out loud. What's the thought process there? Like I really like this part right here that you have to consider the first two numbers at a time rather than just going through it one number at a time. Um, so not the most elegant solution, but it's one that works and it's one that works pretty well. So I will take it. I am happy with that. Um, let's see. Did anyone else come up with anything quicker? Yeah. Okay. Append the port. Yeah. So this person basically just did that. But they. Oh no no no, yeah yeah yeah. This is pretty much the same from what I see. Yeah. All right. Well, that was a great one. I enjoyed that. Yeah. If you watched that, thanks for watching, and I'll see you later.